Alright, this next problem we're going to be doing is from Chapter 4, Problem 40. Problem reads, to drag a 75 kilogram log along the ground at constant velocity, your tractor has to pull it with a horizontal force of 250 newtons. Part A asks us to draw the free body diagram of the log. So this is what we talked about in class as being the force diagram, or what we're going to talk about tomorrow. So let's draw the free body diagram. We just assume that the log is a point particle, right? This is what we talked about in one of the first classes, is that we treat most everything as a point particle, just to make it easier to analyze. So this is a point particle here that has a mass of 75 kilograms. Okay, try to bring that a little bit closer. Mass is 75 kilograms, and we want to move it at some constant velocity, and we are pulling with our tractor. This is the force of the tractor acting on the log. Okay, and that is equal to 250 newtons. All right. Well, it's an odd situation here. It tells us that we're moving it at constant velocity. So it says that the velocity is constant. And if the velocity is constant, there must be another force acting on it. Because if this was the only force acting on it, then that wouldn't. If this is the only force acting on it, there would actually be a net force acting to the right, and then it wouldn't be moving at constant velocity. We would know that there would actually be an acceleration. We can also add some other things. Because this has a mass of 75 kilograms, there's also a force due to gravity, the force of the Earth acting on this log, that is actually equal to its mass times whatever, times the value for gravity. There's also, because the ground isn't being crushed by the log, the ground, there's also a normal force, and I want to be careful that I draw an arrow that's equal length here. So there's a normal force, the force normal here, pushing up. All right, we know that there isn't any vertical acceleration. We wouldn't expect to see the log go flying up in the air just because it's being dragged along the ground. So we know that the weight of the log and the normal force in this case are equal to one another. And if we read along the question a little bit more, it actually, in part B, it even lets us know, it kind of gives us a helpful reminder in case we're a little bit confused, that there is actually another force here. It tells us that there is a frictional force that's pulling to the left. In part B, it says use Newton's laws to determine the force of friction. So we're not actually worried about specifics about the frictional force that's going on, but it's just asking us to consider it as another force. There's another force pulling on the log to the left, and it's asking us to draw the free body diagram. So this is the free body. This is the friction, the force due to friction. Or we might call that maybe the force of the dirt acting on the log. Okay, that's what this frictional force is. That's part A. That's just drawing this free body diagram. And it's important here, I hope it's clear that these vectors are the same length and in opposite directions. So the sum, the net force on all of this stuff, should in fact be 0. How do we know it's 0? Because it's moving at constant velocity. It told us that in the problem. And so if it's moving at constant velocity, its acceleration is going to be 0. All right? Part B then says use Newton's laws to determine the force of friction on the log. Well, if the tractor is pulling it at 250 newtons, and the net force along the x direction here that's moving in some constant velocity is the net force is equal to 0, then we know that the frictional force, the force of this dirt on the log, the force of friction that is acting on that, is also going to be equal to 250 newtons. I think that's pretty clear. And then in C, what is the normal force of the ground on the log? We just drew that as well when we were drawing our free body diagram. That's what's useful about drawing a free body diagram, that makes a lot of sense. You can get a lot of information off of that. So this was part A, just drawing the free body diagram. Then part B, we could just write down what it was. If we wanted to be really particular and write that out, we would write out that the force of the tractor on the log, and that's to the right, so we'll call that a positive value, minus the force of the dirt on the log would be equal to 0 because there's no acceleration in the x direction. Then so adding the force of the dirt on the log to both sides, so it's just that the force of the tractor on the log equals the force of the dirt on the log, which is that frictional force. And since this was 250 newtons, then our force of the dirt on the log is also 250 newtons. Okay, I kind of skipped that, but just in case you need to see that explicitly. So what's the normal force in this case? Well, there's also no acceleration in the vertical direction. So the net forces in the y direction are equal to 0 because there's no acceleration. And so the force of the earth on the log, that's the weight, and we could call that, let's call up positive in this case. So this would actually be a negative value that's pointing down, plus the normal force is equal to 0. Again, we're going to solve for the normal force. So adding the force of the earth on the log to both sides lets us know that the normal force is equal to a positive value of the force of the earth on the log. And we know that the force of the earth on the log is the mass of the log times gravity. And when we plug in the values for that, that is the mass of the log is 75 kilograms, and gravity is 9.8 meters per second squared, or roughly 10 meters per second squared. So it gives us a value here of something around 750 newtons. It's a little bit less than that, but it's a little bit less than that, but that's an approximate. We'll put a little approximate guy value for that. All right. And then part D lets us know that what horizontal force must you exert if you want to give the log an acceleration of 2 meters per second squared? Well, really, we just can use the same expression we have up here, that the force of the tractor on the log minus the force of the dirt on the log is going to be equal to the mass of the log times some positive acceleration. So let's just rewrite that down. That's the force. I'm going to use some abbreviated text here. The force of the tractor on the log minus the force of the dirt on the log, or the frictional force, is equal to the mass of the log times the log's acceleration. All right, and it's telling us for 2 meters per second. So, so it says assume that the frictional force doesn't change. Okay, so the force of the tractor on the log must be equal to, we're going to add the force of the dirt on the log, which is the same as before, 75 kilograms times this acceleration that it wants, 2 meters per second squared, plus 250 newtons. That was our answer from part B above. There it is, 250 newtons. And we're getting to the end of our paper here, so I hope we can get an answer soon. That's basically 2 times 75 would be 150, plus 250 would be 400. So the force that the tractor needs to exert on the log needs to be 400 newtons in order to get an acceleration of 2 meters per second squared. All right? If you have any questions, make sure you post them on the forum.